This funding source provided a little seed money for a small project that was done together with Paul Drazen, one of my former PhD students. He's left the ground. He now works for SpaceX and designs rockets and things like that. But his expertise was nonlinear dynamics, and so we wanted to look at friction pendulum. This is the only slide that's rotated. Happened in the transfer from the stick onto the computer, but if you turn your heads, we'll start with the motivation, talk about the modeling and some results. Yeah, this is rotation because this is nonlinear kinematics. So for those of you that like to linearize, your sine is approximately equal to the angle, which is not true in a pendulum, and certainly not true in my slide here. So this is a little toy pendulum. I think a number of people who've worked here in Richmond recognize this one, this quarter scale pendulum taken apart. It's been used for a lot of things. There's a long history of these models. As I walked over here from my office in the other buildings, I saw this nice poster from Greg Fenves from maybe, I don't know, 15, 20 years ago. And there's some other people. I see Gilbert, who's also worked on this problem. There are a number of different styles of models for modeling pendulums that appear in the codes. There are these sort of original plasticity analogs. So you just kind of look at it as some kind of plasticity problem, and you create some parameters and you fit it. There are also some models out there that are based on the kinetics of what's going on. So you look at it as a bunch of rigid bodies, and they typically work in the plane. All these models that we see, or that we found, they essentially linearize the behavior. But when these things start to move, especially if the puck shoots out and things like that, that's clearly a nonlinear phenomena. And you like to have that in your model. And so really, in a way, that what we see is sort of models are missing the full kinematics of what's possible, while you can also do bidirectional motion. So you see people doing mixing and matching of things. And so this little project was simply to see if we could put everything together and have a model that works for the full range of kinematic possibilities. Would remove a lot of the guesswork that you especially see in the plasticity models, because you're actually modeling the physics of what's going on there. And that, as a consequence of that, you can identify then real failure mechanisms in your designs. So that was kind of the objective here. The way to go about this is relatively straightforward. You just look at what's going on. And this is an example of a triple friction pendulum. You have 5 rigid bodies. Each one has a mass. It has a moment of inertia that we model fully. And so the kinematic states now in the model are the position of the center of mass, and then the rotation, which is a tensor, okay? And the way we do this is we use Euler angles, 1, 2, 3 Euler angles to get the configuration. And this is kind of nice because then you get easy enforcement of the kinematic constraints of the sliding. So, and in particular, what we do is we use relative Euler angles. So we have an Euler system for the first piece, the base piece, and then we use Euler angles relative to its orientation to specify the configuration of the second piece, the third, fourth, and fifth. And this actually simplifies the equations that you get. They're not as nonlinear as you would if you used absolute rotational angles from a fixed reference frame. So everything's sort of co-rotational. You start with the base. You have a set of Euler angles that gives you the configuration of the first piece, and then the second piece is defined off the first piece. And so you can go to as many pieces as you want. And Euler angles have this peculiarity that there's a singularity in the mapping, because you can't map the sphere with a single chart. But that singularity happens at 90-degree rotation, and I don't know of any bearings that go out to 90 degrees, so I think it's pretty good. Also, the other nice thing about this parameterization is it facilitates the expressions for computing the center of mass of the bearings, which you need for the linear momentum balance. Okay, so the other thing that we noticed in a number of the papers that we looked at is that typically the contact force is assumed to be at the center of the bearing piece, but that violates basic equilibrium. You actually have to calculate, there's a distribution of forces, and you have to resolve that into an equivalent system of forces. And I just ripped the mic out here. So you have to actually compute where the effective reaction point is. And so this introduces another set of unknowns into the problem. So you need to do that. So you need another set of Euler angles to compute where the resultant force is going to act on the bearing surface. And so that's what these tildes are. So we have another set of Euler angles. And you just need 2 Euler angles to do this. So you have 2 more. Those are the ones with the tildes on them. So for each piece, you'll have another set of Euler angles. And these are all unknowns in the model. The frictional forces, then, what we've done is just simply use a Coulomb model using Bach-Wen directions, so following some work done by Harvey and Gavin. So you have this classical Bach-Wen thing. And with this also, because we're calculating the reaction point, we also have the rotational friction of the puck. So if the puck spins, you also get the friction force of the spinning in there. And because of the parameterization, these are actually easy things to calculate. They don't add excessive nonlinearity to the system. And then the other nice thing about the Euler angle parameterization is it's also easy to calculate when the pieces will slide and hit the stops. Okay, you have these very simple formulas, dot products between the base vectors of the relative frames. They allow you to calculate what the gap is, and now you can actually calculate the contact on the rim so easy also. So there are a lot of nice things that come out of just doing the problem, I'd say, in the right way. So the overall structure then is sort of based on this relative Euler angular parameterization of the positions. And then you append to that the things that you know, linear and angular momentum balance. What you get is a model for this 5-piece bearing. It has 24 internal parameters. So these are the Euler angle parameterizations of the configurations and also where the contact force resolves. And then the normal forces that you have to calculate too. Okay. The internal degrees of freedom we just calculate using a Dorman and Prince adaptive integration algorithm. So it's a 4th order, 5th order integration algorithm. And there's inside this calculation is a nonlinear algebraic system that you have to resolve. And you can just do that with a straight Newton scheme. So it's a relatively straightforward idea. Just a little bit about the performance here. I'll show you 2 tests of a number of different tests that we did with this model. One is just basic one-dimensional behavior, and we'll compare it to this experiment by Fens and Constantino from 2008. And then we'll look at this classic experiment I think many of you know, which was done by Tracy Becker and Steve over here, where they had a giant slab and they had 4 bearings and they moved their table around in different ways. One of the things that I want to point out before I show the results is that we did 0 fitting in these calculations. So we took the geometry of the bearings that was given and the masses that were measured and the coefficients of friction that were measured. Okay, and so we did nothing else in the model, so nothing else had to be fit. So this is just to show that if you just push the bearing in one direction, it does what you do. So we have these sort of cyclic loops. So this is the motion of the base. This is the force at the top, and then there's just a weight hanging on there. So it's normalized by that weight. And so you have all these different stages of which surface slides on which surface. Okay, and so this just illustrates that, well, you get the right thing. If you compare to the values for a real bearing, so this is the Fens and Constantino case, and so what you have is these displacements are the displacements as you transition from one stage to another. For 1 star, it's transitioning from stage 1 to 2. 2 stars is 2 to 3. This is 3 to 4, 4 to 5. I guess the number of stars look different, and these are the forces at which those transitions occurred. And in this paper by Fens and Constantino, they have this analytical model that they had developed. And actually, the analytical model isn't too bad. This is the experiment here in the middle column. And the last column here is our model. So the response is pretty good. We were really happy that for the first transition, we were able to do much better at the displacement of the transition than the other model, right? So 1.9 versus 2, and the analytical model is giving 0.1. So it's going to give you really bad frequency behavior at the start. So that was a nice result of this model. this is the experiment of Becker and Mahan. And in this experiment, this one is the circular motion. So they're driving the base in a circular pattern. So the two components of the base motion are just sine cosine, 0.1 radians per second. And the black curves here are the measured data. And then the colored lines are the response of the model. Okay, just using the geometry and the measured friction for that bearing. So the response, as you can see, is quite good, not having to do anything. And I should point out that, you know, in this model, all these pieces have all the degrees of freedom, so they can spin, slide in all directions. You can do uplift and all those kinds of things. This is just the cross plot of the force at the top, the x and the y components. Again, the black curve there is the data, and the dotted lines are the model. In this experiment, there's an amplitude A, and that's what the different colors represent. They just kind of step through the amplitudes. The other thing, they actually have a number of tests in this paper. They did single push, they did circular, they had a square pattern, and they also had this thing called a figure 8 pattern, which is basically driving the x and y at a different frequency. So in the y direction, they're going at twice the frequency. And this is the one direction force versus the one direction motion, the two direction force versus the two direction motion. And again, the black lines are the experiment, and the colored lines are from the calculation at increasing amplitudes. And so you can see the response of the model is really quite impressive given what's inside the model itself. So, and this is the cross plot of the 1 and 2 forces. So it also looks quite nice. So this is a completed project, unlike many of the other ones. I forget when we actually did this. So actually, when Colin asked me to talk, I was like, well, I'd like to talk about something else. He says, no, you have to talk about what we funded. So then I started to scratch my head. So okay, I better remember what we did. That was nice reading the paper again. I remembered. Yeah, I know. Yeah, it takes a long time to get a peer report out because they really edit what you write. So if you're not a great writer, you know, Claire is a wonderful editor, but we also write in LaTeX, so then we have this LaTeX word interface with Claire, so maybe there's a little bit of a delay there. But
I'll tell you a secret. I don't sign a thesis anymore until a peer report come out of it. Then I don't need to do any editing.
Okay. So just a quick wrap up on this part of it is, so you know, the model works for this union bidirectional motion. There's no linearization in the kinematics, so it's a full nonlinear kinematic model. And we get good agreement with real experiments. The main assumption is that each piece in the model be axisymmetric. What I've done everything here is spherical surfaces, but if you want to have something that's axisymmetric but non-spherical, you can do that also. And we've also tested on kind of weird bearings where you have an odd combination of friction coefficients. So in Buffalo, they've created all sorts of strange bearings, but not because they're great ideas, but because they test the models. At least I hope that's why they did them. And so we've been able to get good response in those. It's easy to hook this into an FEA code because it's an element with internal degrees of freedom with an internal time integrator, though. So you have to do that. And we've also looked at uplift and loss of compression of the pieces, and so you can get some interesting results if you're interested in that type of thing. And as Khalid pointed out, there is a peer report on this with the excruciating details that came out last year. Okay, so that's part one of the talk. Part two of the talk, I'm going to put my hat on not as a researcher, but as an administrator. And I'd like to say a few words about the SimCenter. Everything can be found at this website, simcenter.design, safe-ci.org. And just a little bit about what the SimCenter is. For those of you that are familiar with the NSF NEARI project, they have a lot of experimental facilities. We are an experimental facility, so an EF, but we're a virtual one. You don't have to come to Berkeley to use the EF. It's an electronic one, and what we do is we produce software applications, and we also have a bunch of educational activities associated with natural hazards engineering. Okay, and the objective here of the center is to advance research, so it's to provide facilities for all of you here that are interested in doing analysis and computation. Just a little bit about the folks that run the place. So the center was the brainchild of Steve Mahan, and it's currently run by a number of us, and Greg Dearline and myself are the co-directors of the center. I'm the PI, and then we have Hassan Karim at Notre Dame, who helps us with all the wind stuff. Laura Lowe's at Washington, who's in charge of the educational components. Camille Crittenden helps us with computer science aspects. Matt Schottler is our associate director of everything, basically, and then Frank is our chief information and technology officer. The folks that are really doing the work is our crew of postdocs. So we have 6 postdocs with us right now. Michael Gardner hasn't quite started yet, but I see a couple people that need to sign his dissertation very soon. Oh, all right. Okay, so Michael gets 5 days of vacation before he starts, I guess. He had wanted 3 weeks originally, but so that's Michael. Adam is at Stanford, and Peter Simpliski is at Notre Dame, and then Nikhil Chaofeng and YL are here over in the other building. So we have a nice group of people with a varied set of talents that are helping out. And if you interact with the SimCenter, you're likely interacting with one of these people. There's also a large number of faculty participants spread out across the country who deal with various aspects of natural hazards engineering and its simulation. And so hopefully if you're in the center, your name is up here. Let's see, let me go to UW. I do see Pedro's name. So I saw Pedro put his glasses on, so I thought I'd better check to see if I got his name there. But so we have a large group of people that represent all sorts of things. So, you know, we have the people under the ground. There's John. We have social scientist Paul Waddell. There's quite a Anne Margaret in Georgia. So we have a wide variety of people helping us out. So these are also people that you can interact with if you're interested in the center. So just the goals, we're looking to develop a computational framework to support decision making in natural hazards engineering. And so we're doing everything from looking at behavior components to behavior of regions. Okay, so we have a lot of software that we're developing, and it's supposed to, if you're interested in something small, you can do it. If you're interested in something big, we have software to help you do it. We're developing a framework, and we're seeding that framework with existing simulation tools, but the framework is extendable and flexible so that, you know, I was talking with Kenichi earlier today, is that, you know, he has this agent-based modeling things, and we have something that does that using UrbanSim, but we're developing a framework where he can plug his thing in too, and then we can use his instead of UrbanSim. So it depends on the questions that you want to answer. So the other thing I mentioned the center's doing is education, and so we're also trying to build kind of an ecosystem that fosters collaboration between people working in this area. And so we have a natural hazards engineering component, education component. So if you go to the website, we have webinars for students and things like that, and things to teach people about various aspects. And so if you'd like to give a webinar, we'd like to hear from you too. So if there's something that you're interested in communicating to the community. Just a little bit about the software tools that are currently under development. So the first one is a UQFEM tool. And Pedro mentioned this tool in his talk yesterday. It's just simply a very simple tool that allows you to interface to finite element codes or even Gauss point drivers and other types of things, and it does uncertainty quantification for you. So you can pick distributions of parameters and punch a button, and it will run. And if you want to run a big job, it will launch it on the cloud for you. There's an earthquake engineering UQ tool that's to provide response of buildings to earthquake events. It grabs ground motions for you, collections of ground motions, I guess from pure NGA and other types of things like that. Eventually, it also has a plugin, so at some point if you want to put your own ground motion model in, you can do that. So you don't have to use downloaded records. We have a computational wind engineering tool. Right now it does bluff bodies. And so that's to calculate response to wind events. We deal mainly with seismic events, wind events, and water, so tsunami. Okay, we don't do fire because NSF bans us from doing that for some reason. We also have a performance-based engineering tool, which is a combination of pieces. So we don't just develop single tools, we develop tool chains and workflows so that you can seamlessly hook together various types of tools. So it has the earthquake engineering tool hooked together with the wind tool, so if you want to do multi-hazard, and also look at downtime and loss. So we have downtime and loss software too in the system. And then there's also the RDT tool, and Frank, remind me again what the acronym stands for? Resilience Decision Tool. See, that's what happens when you become a manager. You don't even know what the acronyms mean. So that's something that's coming down the road. So, but that's for the planners and things like that. And we're looking at other things, and if people have grand ideas or pieces of software that they develop that they think they'd like to expose to the broader community, we're happy to work with you. So all of our software is open source. You can grab it from GitHub and compile and use it extended, but you can also grab compiled versions and just run them. And so, but just going back to the big picture is, we're developing a framework that allows all these pieces to be hooked together seamlessly, so that you and your students, or if you're a student or whatever, you don't have to do that grunt work. It's there for you and it runs. So, one of the things that we see, and one of the things NSF saw, was that there's lots of isolated pieces of software being developed, but nobody gets to reuse them. Okay, and so the big point here is that stuff has a life. There's somebody curating it, making sure it works, and that's us. And for people doing research, it's supposed to be flexible and extensible. And just a little bit about how this stuff runs. When you get our tools, you can run them on your laptop. I've even done it. I ran a computational wind calculation the other day, much to my surprise, and it even worked. So that was pretty good. But if you want, you can also fire off the jobs at TAC in Texas. So it runs, I guess, on Stampede 2. And you can run your jobs in parallel and things like that. So, and that's built into the interface to the tools. Real quick about release schedules. So UQ-FEM tool is out. The computational wind tool is out. The earthquake engineering UQ tool will be coming out in August. And the PBE tool with an earthquake workflow will also come out this fall. In these boxes, you'll see the little letter AI. We heard a bit about AI stuff yesterday. Many of these tools have facilities to auto-build models for you. Okay, so if you want to do regional simulations or something, we're building in facilities so you can auto-build reasonable models. We're also have some more, I guess, far-reaching type of AI tools that we're trying to develop, things that will take BIM files and actually create analysis models for you too. Because especially those of you who are interested in regional types of things, it's a total hassle of how do you get the analysis models for everything. So we're trying to work out schemes by which we use AI to generate models automatically from things like Google Street View and satellite imagery and other things. So we heard some of that stuff yesterday. And there are limitations to what you can do there, but we'll provide base models for you. And I think there's also opens up an exciting area of research for people to kind of improve upon that technology. How do you make that stuff work better? So we'll have the infrastructure. You can try out your ideas. Okay. those are the research tools. The workflow things for regional, we have this regional earthquake test bed that was released, and it goes actually from rupture, simulation of ground motion in the Bay Area. It has, I think it's 1.8 million buildings in it, and it goes all the way to downtime and loss. Okay, and so that's something that you can play with and do things with. It's a bit of a heroic calculation, I guess. Our first shot at it brought the supercomputer center to its knees, but it was a learning process. We learned some things. And much of the stuff which is sort of more regional, you'll see the dates are further out because these are more complicated things to put together. The RDD tool is several years away. The educational apps, there's a multi-degree of freedom tool where you can put earthquake records and see how different types of buildings respond. There's a pile group tool. You can design pile groups and put different layers of soils, and you can see how they respond. There's a tool, EVW. We had a hard time with the name for this. This allows you to compare the responsive buildings to wind and earthquake loads and see how they respond with a similar design. And so there's a wind selection tool, kind of like we have ground motion tools. There's a wind selection tool in that. There's a new tool that will be coming out. Barbara Simpson's working on a brace frame modeling tool also. So those are out. One thing, this is just a quick screenshot of some of the tools here. So you can see that for those of you that have struggled a little bit with OpenSeas a bit, we actually have GUIs for the tools. So, people like that, but you also have source so you can edit them. There are also manuals for the tools. Some manuals are better than others, kind of depends on who authored them. But these are, these were designed, these are the ed tools here. They were designed for education, but in my mind, you can actually do some nice little research projects with them too. So, and they're easy, you can download them, they're widgets, they'll run local on your computer, and so they're really good for educational things, but you can also do real things too. So this is the, Pedro worked on this, I guess, the pile group tool. So you can design your piles, put your soil layers in here, you can push on the pile cap, you can see the response, and everything happens in real time. As you make changes, you see the response of the system. I guess I'm not sure what that is. What is that one on the side there? It's plotting, I guess probably shear, yeah, okay. Yeah, and this is the MDOF tool. You can set the stories, the floor weights. You can pick a ground, you can pick a record, and then it'll show you the time history as it goes along, calculates it very quickly locally on your computer. This is the wind case down here.
One interesting thing is that you can run this educationally, but then you can say generate a TCL file for OpenSeas, and then you can go from there in the research, modifying the TCL file. And at least you have something to start with.
Yeah. So we have a lot of these things up there. Everything is essentially version 1.0 except for the pile group tool because Pedro's really quick at this. I guess so he's in version 2 already, advising us. But so we really encourage you to just download the stuff and run it and use it. And then we're happy to start to talk to people about how they want to interact. So if you have software that you'd like people to use, because we do research and develop all these analysis tools, and the idea is people use them. So if you believe in that, this is a place where we can get your tools out to a wide audience. But also, if you just want to use them, or if you want to see modifications, let us know. We really want to know what the researchers want to do, and we want to help facilitate your research. So our objective, our job is to facilitate research through computation. So we're here for that. So, and I'll stop there.